Assalamualaikum. So today we're going to continue our topic in metal cutting, that is on the study of chip formation and classifications of chips. And as introductions, we know that the cutting operations are involved with the removal of microscopic chips, usually in the forms of ribbons or particles. And the chip, tool, and workpieces are actually hot to touch. So considerable thermal energy is associated with the cutting process. And the purpose of this topic is to bring together observations on the form of chips. And what we will see in the next slides are on the types of chips that have been observed, the frictions between the chip and the tool, and as well as the work hardening behavior of the machine material. The formations of all types of chips are actually involved of the shearing of the work material in the region of a plane that is extending from the tool edge to the positions where the upper surface of the chip leaves the work surface, as you can see in the figure. Okay, a very large amount of strains is actually take place in these regions in a very short interval of time, and actually not all metals and alloys can withstand this strain without fracture. So gray cast iron chips, for examples, are always fragmented, and the chips of more ductile materials may be produced as segments, particularly at very low cutting speed. The chip can be in various shape and size when in the industrial machining operations, and the temperature of the cutting tool may reach very high, particularly when a heavy cut is done at high speed. And this can be evident when the work or tool is touched by the presence of temper colors of the chip, work, or tool, or it can be seen in the loss of hardness of the tool point, with the loss geometry of the tool and failure due to the excessive flow at the cutting edge. So when the tool face frictions is decreased, there will be an increase in shear angle and an accompanying decrease in the thickness of the chip. So as shown in the figure, the plastic strain in the chip decreases as the shear angle increases. The length of the shear plane is actually to be significantly decreased as the shear angle increases. And the force along the shear plane will increase as the area of the shear plane increases, by assuming that the shear stress on the shear plane remains constant. The first step in considerations of the mechanics of chip formations is to identify correctly the type of chip involved. It can be in terms of steady state, BUE that is built up age, or it can be discontinuous, wavy or sawtooth. And if at the outset of a metal cutting analysis, an incorrect chip type is assumed, the results obtained may be misleading. So it is extremely difficult to predict the type of chip that will form, and the best way of determining this one is through experimentally. And a very few cuts under the conditions of interest will clearly indicate the type of chips involved and the type of analysis to be applied. The friction between the chip and the tool is actually plays a significant role in the cutting process. And these frictions may be reduced by improve the tool finish as well as sharpness of the cutting edge. We can also improve or use low friction work or tool materials. We can increase the cutting speed, increase the rake angle, and also with the use of cutting fluid. There are different types of chips that is formed in terms of shape or sizes, which are produced by machining. And these chips are also depending on the type of machining process, which can be in terms of continuous process, that is turning or boring, or it can be in terms of depending on the intermittent cutting process, that is through the milling machining. And the chips can also be formed depending on the work materials properties or type, whether the material is a brittle type or the ductile type. Others chips can be formed due to the type of cutting tool geometry, and the geometry of the rectangles, cutting angles, and so forth. And other than that, the chips can be depending upon the levels of cutting velocity, and also the fit, whether we use a low, medium, or high, and also the type of fluid, whether we use fluid assistance or fluid applications, and also method of applications on the fluid applications. And the basic major types of chips and the conditions are generally under such types of chips that is shown on the figure. For the irregular size and shape, the work materials usually by the brittle materials like the gray cast irons. And for the discontinuous regular size and shape, the work materials can be from the type of ductile type materials. And also probably it use large feed rate, negative to rake angle, and also can be presence due to the cutting fluid, whether it's absence or inadequacy of the cutting fluid. And this is the examples on the continuous type with and without build-up edge, and also the segmented type of the chips formations. For the continuous type without the build-up edge, usually the work material is the ductile type, and the cutting velocity used is usually high, feed rate is in low conditions, and the tool geometry or rake angle use is usually positive and quite large rake angle, and it is using the cutting fluid applications. For the continuous type with build-up edge, it is using the ductile type material, and for the velocities usually in a medium rate, feed rate usually in a medium or large rate of the feed. And for this one, it does not use the cutting fluid. Okay, and for the segmented type, the work material is usually a semi-ductile materials, and cutting velocity usually in a low to medium range. Feed rate is from the medium to large range, and it usually has the tool rake angle with a negative angle, and this one does not use the cutting fluid. Continuous chips may adopt many shapes. It can be in a straight, rectangle, or with different types of helix. Often they have considerable strength, and control of shape is one of the problems that is confronting mechanics and tool designers. Continuous and discontinuous chips are not two sharply defined categories. Every shade of gradations between the two types it can be observed. The longitudinal shape of continuous chips can be modified by mechanical means, for example by groovings in the tool rake face, which helps to curl the chip into helix form. And the cross sections of the chips and their thickness are quite important in the analysis of metal cutting, and usually considered in some of the details. And for the purpose of studying chip formations, relation to the basic principles of metal cutting, it is very useful to start with the simplest possible cutting conditions, that is to be consistent with maintaining the essential features common to these operations. So what you are seeing in this slide are some of the examples type of chips that is formed or produced at a very high cutting speeds. For the chips formed on your right side is actually when we use the chip breaker. So at relatively lower speeds, type 2 chips are actually produced, which is at the bottom left corner. And at the right side bottom corner of this slide is a chip that is formed when chips are used. And on this figure, you are seeing chips that are formed at the lowest speeds with equal curl radius, that is shown at the type 3. And at the right side are the chips that is formed when chip breakers are used. And for the type 4 chips, it is produced at lower depths and it has irregular curves. And for the radius of curvature is usually irregular. Okay, and for the type 5 chips, it is curled chips with disordered blocks that is produced at low depth of cut. Next are the type 6, which are in a coiled type chips. And on the right side, A, B are the formed as the result of curling when chip breakers are used. So when the chip breakers are used, chips are formed with having several turns, whether it is single turns or even half turns. The formation of chip by shearing action at the shear plane is one of the aspects of metal cutting which has attracted most attention from those people who have attempted analysis of machining. And the list equal importance of the understanding of machinability and performance of cutting tools is actually on the movement of the chip and the work materials across the faces and around the edge of the tool. In most analysis, this one has been treated as a classical friction situation in which frictional forces tend to restrain movement across the two surfaces, and the forces have considered in terms of coefficients of friction, that is between the tool and the work materials. But detail on the studies of the tool or work interface have shown that this approach is inappropriate to most metal cutting conditions. And it is unnecessary at this stage to explain why classical friction concept do not apply, and to suggest a more suitable model for this analyzing situation. The concept of coefficients of friction is actually taken from the sliding of one solid surface over another, and the force that is required to initiate or continue sliding is actually proportional to the normal force that is on the interface, which is the sliding is taken place. And these coefficients of friction is dependent only on these forces and is independent of the sliding area of the two areas. Underloading conditions are used in engineering sliding mechanisms. The real contact area is very small, often less than 1/100th of the apparent area of the sliding surfaces. And the mean stress acting on the real contact area supporting the load is equal to the yield stress of the material. If the compressive force normal to the interface is doubled, the real contacts supporting the load are plastically deformed until they doubled in area, so that the mean stress on them remains constant. In the areas of real contact, the atoms of the two surfaces are brought within range of their very strong attractive forces, meaning that they are atomically bonded, meaning they are very bonded. And the frictional force is that the force that is required to shear these areas um, of the real contact. And this friction force is proportional to the real contact area, and therefore also proportional to the normal force. In engineering sliding mechanisms, the coefficients of friction, that is F over N, is therefore a useful concept. That is, under conditions where the normal stress on the apparent contact area is very small compared with the yield stress of the materials. So when the normal force is increased to such an extent that the real area of contact is a large proportion to the apparent contact area, it is no longer possible for the real contact area to increase proportionately to the load. In the extreme case, where the two surfaces are completely in contact, the real area of contact becomes independent of the normal force, and the frictional force becomes that required to shear the material across the whole interface. So when two materials of different strengths are in contact, as in metal cutting, the force required to move one body over the other becomes the required force to shear the weaker of the two materials across the whole area. And this force is almost independent to the normal force, but is directly proportional to the apparent area of contact, meaning that a relationship directly opposed to that classical friction concepts. Thus, it is important to know that what conditions exist at the interface between the tool and the work material during the cutting. And this is actually quite a very difficult region to investigate. And few significant observations can be made when cutting is in progress. Thus, the conditions existing must be inferred from studies of the interface after cutting has stopped, and also from measurements of stress and temperature. The conclusions presented here are some of the deduced from plenty of research studies, mainly by optical and electron microscopy, of the interface between the work material and the tool after it is being used in a wide variety of cutting conditions, in which you will see in the subsequent slides. Evidence can be comes from worn tools, from the quick stop sections, and as well as from the chips. When cutting is stopped by disengaging the feed and withdrawing the tool, layers of the work materials are commonly, but not always, can be observed on the worn tool surfaces, and microsections through these surfaces can preserve details of the interface. Special metallographic techniques are essential to prevent rounding of the edge where the tool is in contact with a much softer, thin layer of work materials. And the shown figure on the slide is actually a photomicrograph of sections through the cutting edge of the cemented carbide tool that is used to cut steels. And the white area is actually the residual, okay, the residual steel layer that is attached to the cutting edge, that is slightly rounded, and the tool rake face horizontal and down the one flank. The two surfaces actually remain firmly attached during the grinding and polishing of the metallographic sections. And any gap larger than 0.1 micrometer, it can be visible at the magnifications in this photomicrograph, but no such gap can be seen. It is unlikely that a gap exists since none of the lubricant used in polishing is oozed out afterwards.